Hello, everyone. Welcome to the MIF seminar. It's a great pleasure to introduce Soledad Villar, who is a professor at Johns Hopkins University in the US. And today, Soledad will talk about invariant machine learning on point clouds and Galois theory. Over to you, Soledad, please.
Well, thank you for the invitation. I'm going to talk about invariant machine learning on point clouds, and some of the techniques that we will use are from Galois theory. Please ask questions and just let me know if there's something that I should explain more, or I don't know. I'm very open to taking questions and discussing the things that I want to talk about. So as a motivation, I'm going to describe deep learning architectures and the relationship with symmetries. I think that symmetries have been something that showed up in machine learning for a long time. And now they give you a good design for machine learning models, especially for machine learning for natural sciences. So, but not only for natural sciences. And so there have been a lot of machine learning models that have used symmetries. And I will argue that most of them have some form of implicit or explicit symmetries. For example, convolutional neural networks are invariant with respect to, or equivariant with respect to translations. And recurrent neural networks also have some time translation symmetry encoded on them. Graph neural networks, which is something that Vitaly's group use a lot for doing computational chemistry and lattices, have an explicit symmetry, which has to do with the fact that if you have a graph and you code it as an adjacency matrix, the representation of the graph is not unique. So there's a permutation symmetry that is natural in these graph neural networks architectures and is encoded by design. And also transformers can be thought as having permutation symmetries if you don't consider the position encoding. So all of these, like, very widely used through the history of deep learning models, have some form of symmetries. And or sometimes they encode approximate symmetries. But basically what we want to have is a machine learning model that is aware of the structure of the problems that one wants to solve and exploit that for efficiency and for giving you a good inductive bias. So you can look at for instance, the geometric deep learning book that makes a lot of emphasis, and this describes many uses of symmetries and other structures like geometric structures in the design of machine learning models. And this is particularly important for well-structured problems, like problems that show up in sciences. And in the physical sciences, there's two types of symmetries. The symmetries that come from the regularities of the physics. So say you have a system that conserves energy, and that conservation of energy is linked to a time translation symmetry due to Noether's theorem. So there's like a relationship between conserved quantities and symmetries that are satisfied by the physics. And those are called the active symmetries in physics. But also there's some symmetries known as passive symmetries within the physics literature. And these symmetries have to do with the fact that when we have a physical system, like you can think of a pendulum, or I don't know, the Earth or the universe, when we encode this object mathematically, the representation of that object mathematically is not unique. There are many choices one makes. One makes the choice of the coordinate system, the unit system, etc. And changing these coordinates or changing these representations, mathematical representations of the object, doesn't change the object itself. So if one does a transformation of the inputs of your model, and then the outputs of your model should transform in the same way. That is a very huge group. You can think of the group of reparametrizations is a group that acts in the space, and there's an equivariance with respect to that. And like mathematically or in machine learning, we don't know how to express all these symmetries, but there's a very large set of symmetries that we know how to express. And the claim is that if you make a machine learning model for science, then these models should be consistent with the symmetries that the problem has. So this should be, for instance, coordinate free. And that mathematically, you can even write a theorem saying, like, if your problem has these symmetries and your machine learning model has the corresponding symmetries, then it gains something in terms of sample complexity. So you can learn with fewer number of data points, and you can learn something in terms of generalization error. You can generalize better if you impose the symmetries of the problem. And that can be mathematically quantified, and there are papers that do that. I'm happy to provide you references if you want at the end. But basically, just imposing the symmetries that the problem has is something that is a good idea because it reduces the complexity of the problem, and you can learn with fewer samples and with a smaller error. However, there's also the optimization question, which is like, if I parameterize my machine learning model that satisfies these symmetries, then when I do stochastic gradient descent, or if I do some like Adam optimization, then will I converge to something that works well? Will I converge to something that generalizes outside my training set? And that's something that is not fully understood for many of these models that satisfy symmetry. So there's a lot of mathematical questions there that are very important. So yeah, but there's a literature about it, and I think someone put in the chat the book of, I imagine that is a geometric deep learning book, but I don't know. Good. So in this talk, I'm going to focus on one specific problem within this whole space. And the problem that I'm going to focus on is machine learning on point clouds. And this is a topic that has been studied very broadly from many points of view. It has many applications to chemistry, to astronomy, to material sciences. And I know that Vitaly and other people have done a lot of work in this space. I'm not going to claim that I have the best model of machine learning on point clouds, not at all. The opposite, I'm just going to give you some mathematical theory that one can use to think about these problems in just like a different perspective on the same problems. But I'm not claiming that anything that I'm doing is better than any of these papers that I have here. It's just a different mathematical perspective to think about these problems. Yeah, so just a caveat. Yeah. So, so basically, the motivation when I started thinking about this problem came from interactions with a group of people that work in cosmology. So in particular, this was done with my collaborator, David Hogg at NYU, whose PhD student at the time, Kate Story Fisher, wrote her thesis, and now she graduated and she's a postdoc at Stanford. She wrote her thesis on part of her thesis had to do with like invariant functions on point clouds that she used to do regressions for cosmological simulations. So the idea is the following. She has, there's like these cosmological simulations that basically do a simulation of like the evolution of the universe from from the initial conditions of the universe. And basically what they want to understand is like, how does the universe evolve with time from like these initial conditions? And there's two types of simulations. One simulations that are called dark matter only simulations that basically just assume that you have an initial set of points, particles, and then they evolve just through gravity, through gravitational interactions between them. However, the universe is more complex than that, and there's not only gravitational interactions, but also there's some electromagnetic interactions and interactions of other forms that are way more complex to simulate. And so if you want to have like a more sophisticated model of the universe, then you would need to add the hydrodynamics of the universe, and these simulations are way more expensive. So these, you can think of the dark matter only simulations are the cheap simulations, and the hydrodynamic simulations are the expensive simulations. So you can only do small hydrodynamic simulations with the computational resources that she had, and the dark matter only simulations can be done with way more particles. So something that she wanted to do in her PhD thesis was to learn what were the properties of stellar halos or galaxy halos that she would have obtained if she was able to run full hydrodynamic simulations. So she had only the dark matter only simulations, and she wanted to learn the properties of the simulations that were the more sophisticated simulations. So basically, it was just a regression problem on point clouds. So she wanted to predict the properties of galaxies from these dark matter only simulations, and the ground truths will come from these hydrodynamic simulations that can only be done in like a very small, in very specific settings because they're very expensive. And so in these point clouds, you will have that this like simulation of the universe, all the points are exchangeable. So there's a permutation symmetry. And for these point clouds, what she wanted to learn was the mass of galaxies. And this is something that is invariant with respect to translations and rotations. Just like what matters is the shape and the density of these point clouds. So mathematically, we can write the point cloud as endpoints in RD. Here, RD will be R3. And she works in phase space, so it's like R3 plus R3. Yes.
Soledad, could I ask about galaxies on the previous slide? Am I right that the basic input from this galaxy data is simply a collection of three-dimensional coordinates? So one point in a three-dimensional space per galaxy, or is it per star?
So it's in phase space, so it's positions and velocities of these points. And these points come from a cosmological simulation. So the initial conditions is basically all the points, all the particles come from something that is like a lattice, like all the points in the same in a lattice with some noise. And depending on the noise, the evolution goes to one direction or another direction. Oops. I think my iPad disconnected. I'll try to connect.
No problem. We will wait. Okay.
Sorry.
Okay. No rush. No problem.
Yeah, it's just I don't know why it happened, but it did disconnect. Okay, I think.
Okay, so yeah, so in this simulation, then we have points probably in a big cube, and every point, as you say, represents a galaxy. So we have, say, a
no,
center.
The points don't represent a galaxy. So the galaxies are clusters of points.
Okay, so a star. Then every point.
Maybe I'm not exactly sure what these points represent, because they cluster out. So they start all spaced out, and then with the gravity and with the evolution of the system, they cluster and they form clusters that they're known as halos. And these halos include galaxies.
Okay.
I'm not an expert in the cosmology side of the project, but basically that's what it is. Can you see my slides now?
Your screen, yes, and hopefully, now slides. Thank you.
Great. But the points are in positions and velocities. So in practice, you have 6 dimensions, but the action of the group that you care is orthogonal, is the orthogonal group in dimension 3, acting on pairs. What happened here? Okay, so the setting is the following. So you have these point clouds. So there are n points in dimension d. Let's abstract it to like a mathematical setting, and basically you want to be invariant with respect to translations and permutations and rotations. So ED is orthogonal transformations plus translations, and then you have permutations, meaning that all the points are exchangeable. So in practice, you only do translations in the space coordinates, and then the velocity coordinates do not translate, right? So yeah, that's the reasonable thing to do. So in order to deal with translations, the trick or like the technique that is more reasonable to use is to basically just take your points and then subtract the center of mass, and then every point is like you choose like one representative per translation orbit in some way, right? So given your point cloud, you translate it to the origin, the center of mass is in the origin, and then you can just do your machine learning method with that. That technique can be done for many groups, and in the literature of invariant machine learning is known as canonicalization. So basically, you have a systematic way of choosing one representative per orbit, and then you put everything in these canonical coordinates, and then you think of like your model applied to your objects in this canonical representation. That is a simple way to deal with translations. Great. Then we also care about rotations and reflections. So the orthogonal group, which is here would be like the D by D matrices, so that R transpose is equal to R transpose R, which is equal to the identity, just the orthogonal transformations. And these orthogonal transformations correspond to the isometries, well, translations and orthogonal transformations, but say orthogonal transformations correspond to the isometries of RD that fix the origin. Linear transformations. And so in order to write the functions that are invariant with respect to the orthogonal group, what we can do is we can use the very classical invariant theory tools, which are known as the first fundamental theorem for invariant theory for OD. And basically the idea is the following. So what is an OD invariant function that takes n vectors in RD and outputs a scalar? Is a function that if you take all your inputs and apply the same orthogonal transformation to each of the inputs, the function doesn't change. So you say if I have a point cloud, I rotate all the points in my point cloud, then the output of the function doesn't change. So for instance, you can think that I have this point cloud and I want to compute the energy of this point cloud, the total energy of this point cloud. If I apply a rotation to all the points in the point cloud, the energy doesn't change. And the first fundamental theorem of OD says that a function that takes n vectors in RD and outputs a scalar is invariant if and only if you can write it as a function of the inner products of the input vectors. Intuitively, this makes sense because if you have a point cloud and then you compute all the inner products and then you do a rotation, the inner products don't change or on an orthogonal transformation. And then the rest of the first fundamental theorem would be to prove that that's sufficient. So if you have something that preserves all the inner products, then any function that is invariant with respect to these orthogonal transformations can be written as a function of the inner products, basically. So from the inner products, you can recover the point cloud, modulo the orthogonal transformation. And so mathematically, if you're a mathematician, you can write it with a commutative diagram, typically. So basically, you have endpoints in RD, and a function that takes endpoints in OD and puts a scalar that is orthogonal, can be written as the composition of a function that first extracts these features, which are the n by n inner products, and then it writes the function as a function of the n by n inner products. And that is like that as classical characterization for the orthogonal invariant functions. And similar characterizations from this classical invariant theory exist for other classical Lie groups like the Lorentz group, rotations. The rotations are similar, but a little bit more complicated. The symplectic group, the unitary group, etc. And then at the end, I can show you a little bit how to extend this construction to write equivariant functions instead of invariant functions. But the focus of this talk is invariant functions. Great. Questions so far? There's something in the chat.
Soledad, could you briefly remind us what is the Lorentz group?
Yeah. So the Lorentz group is a group that is used for special relativity, and basically you write it as the inner product in the Lorentz group takes, like, every point has the space coordinates and the time coordinates, and then the inner product is the inner product in space minus the product in the times. So basically, if you have like say x1, x2, x3, t, and x1 prime, x2 prime, x3 prime, t prime, the inner product, the Minkowski inner product between these two things is equal to like x1 prime plus x2 prime plus x3 prime minus t prime. And so the functions that are going to be invariant with respect to this Lorentz transformation are going to be functions of the inner products with respect to this specific inner product.
Okay, so the Lorentz group consists of all transformations that preserve this bilinear form.
Yes, so you can write it, like if you want to write it in this, using this notation here, this is the OD. OD. So the Lorentz group would be like, you would write this delta matrix, which is going to be 1, 1, 1, negative 1. And so it's going to be the matrices Q, so that Q delta Q transpose is equal to, gamma. Yeah. So this basically is the transformations that preserve this bilinear form, not the other bilinear form. And so this is the transformations that are used in special relativity with the transformations that preserve, like that preserve the metric of space-time.
Okay, yeah, thank you, Soledad.
Yeah, good. So so far, I show you how to do translations and orthogonal transformations, so rotations and reflections. And then the next step is to work with permutations. So say that every point is exchangeable. All the points are exchangeable. So the idea is that we have the point cloud that we represent as a D by N matrix. And then we have two groups acting on this point cloud. On the left, we have the orthogonal transformation, so we can apply a rotation to the D coordinates, as I had in this slide here, acting on this point cloud on the left. But on the right, I can act by the permutation. So changing the order of the columns of this matrix doesn't change the output of the of the problem, like the model, the output of the model, right? And so so how do we do this? So we want to find a function that is invariant with respect to orthogonal transformations and with respect to permutations. So since we already know how to deal with orthogonal transformations, then we're going to do invariant with respect to orthogonal transformations, and then we're going to see what happens with the permutation action afterwards. So we have a point cloud, and we know from the previous slide that it's invariant if and only if the function is a function of the inner products. So this is f of b is equal to some f tilde of b transpose b. This is the Gram matrix of your points. This is an n by n matrix, right? And so if I had a permutation that acted on my point cloud, then the permutation action would look like the action on this Gram matrix by permuting rows and columns, right? Because I acted on the right by descent, but then when I take the inner products, then the permutation acts on the right and on the left by its transpose. And so basically what we want to do is we want a function of the Gram matrix that is invariant with respect of permutations of rows and columns. So this is the same symmetry than, for instance, the graph isomorphism problem, and it's the same symmetry that graph neural networks implement by design. When you are doing like a regression problem on graphs. And we are not in this project that I described here, we don't use graph neural networks, but you could use graph neural networks here, but with the caveat that you would need to use graph neural networks on a graph that is the graph consisting on the weighted graph of like the inner products of all the points in your point cloud. So you start with n points in dimension D, and then you have to write the matrix of inner product, which is n by n, which can be very large. And so that's one reason why we're not going to use necessarily graph neural networks. So, and we're going to use some techniques from invariant theory, and I'm going to show you how that works. So basically, why do we use invariant theory instead of graph neural networks? Well, because constructing the graph has O of n squared complexity. And I'll show you at the end some way to do it using invariant functions that only require O of n times d. And you can think that d in this cosmology problem is like 3, and n can be like thousands or millions of points. So it does reduce a lot. In some cases, you can show that there's some improved expressivity over vanilla message passing neural networks. And there are interesting mathematical tools that could potentially be used more broadly. And this is where Galois theory enters. And I'm going to tell you how to do that in the next slide. So what is Galois theory? So the idea is the following. So we have the group of permutations acting by conjugation in these n by n matrices, permuting rows and columns. And then what I want to do is I want to write the functions that are invariant with respect to this group action. Well, it's not that easy to write the functions that are invariant with respect to the group action, but I can find a larger group that I know much easy, like that the invariant functions with respect to this group are much easier to characterize. So the group that I consider is the group of permutations that permute independently a diagonal element to a diagonal element and an off-diagonal element to an off-diagonal element. You know that if you permute rows and columns of a matrix, all the diagonals have to go to a diagonal, and all the off-diagonals have to go to an off-diagonal. But not every transformation that sends an off-diagonal element to an off-diagonal element and a diagonal element to a diagonal element corresponds to rows and columns consistent transformation, because maybe you would do something like this, like moving independently diagonal to diagonal and off diagonal to off diagonal, and then what you get at the end is inconsistent with permuting rows and columns, right? So you can think of it as this small group is a subgroup of this big group, and so the invariant functions with respect to this group is larger than the invariant functions with respect to that group, because the correspondence between invariant functions and groups, it goes the opposite way. So if this is inside that, then the invariant functions with respect to this has as a subset the invariant functions with respect to the larger group. Right? You can think of it as like more constraints or fewer constraints. So if you have more constraints, the functions that satisfy more constraints is a smaller set than the functions that satisfy the less constraints. And so if you do this independent change of diagonal to diagonal and off diagonal to off diagonal, then basically the invariant functions are very easy to write. It's just the functions on like the set of the diagonals and the functions on the set of the off diagonals. You can write it as the elementary symmetric polynomials on diagonal elements and the elementary symmetric polynomials on off diagonal elements. This is how you can do it. And so what does the Galois theory tell you? And please let me know if someone didn't know what Galois theory is. I'm sure that many people at least know the story behind the Galois theory, because it's like a very well-known story about this Galois who wrote this theory when he was very young, and then he died very young in a duel in France. And I think he was like 21 years old when he died, and he had written some manuscript on like this correspondence between fields and groups. And then, well, maybe not in this language, and he couldn't get it published when he was alive. But then afterwards, someone dig up his papers and they found this, and it became like a very big thing in the history of mathematics. So it's like a very interesting story that you could read about. Anyway, so what does the Galois theory tell you? It tells you that if we construct a set of invariants that are only fixed by the desired group, so here the smaller group, so that no other bigger group fixes all the invariant, then all these invariants generate the field of invariant functions, right? So basically we have this group Sn, which is a smaller group, so it has more invariants, and this is the bigger group that has fewer invariants. So if I start from here and then I write all the functions that are invariant with respect to this, and they're not invariant with respect to bigger groups than this, then with that, I can generate the field of invariant functions. This is not the way Galois theory is expressed in general, but this is like an equivalent way of thinking about these ideas in this context. The theory can be written in like a different language, but in this context here, we can think, what does Galois theory tell us for this specific problem? It tells us that we start with the invariants with respect to the larger group, and then if we can construct some invariants that are only invariant with respect to the smaller groups, meaning that they are not fixed by anything bigger than that, then those will generate the field of invariant functions. And once that you can generate the field of invariant functions, then Rosenschmitt's theorem tells us that with those field generators, then we can identify all the orbits of the group action, except for a small bad set, which is like the zeros of a system of equations. So they have They're a closed set, which is measures 0 and invariant. So the idea is that, yeah, we can construct the field of invariant functions using constructing some specific elements, and with that we can generate we can identify all the orbits, almost all the orbits. And then there's a technique, the standard technique from machine learning, that if you can separate all the orbits or almost all the orbits, then using some machine learning model on top of it, then you are able to universally approximate all the functions that are invariant with respect to that, using like things like stone bias. But basically that's the idea. Is this more or less clear? Maybe it will be more clear when I go to this slide. So what is this slide telling me? Okay, so first I start with the bigger group, which is the group that I understand well. This is the group of that acts sending diagonal to diagonal elements and off diagonal to off diagonal elements. That is that group has a corresponding field of invariant functions that is given by the symmetric polynomials that send diagonal to diagonal and off diagonal to off diagonal. So the symmetric polynomials, the invariance on the diagonals and the invariance on the off diagonals, right? And so this field is a subfield of the field of rational functions on the entries of the matrix, right? And so if I can construct some element that is only fixed by this action of permutations, then I can generate the field of invariant functions with respect to the action of permutations by conjugation, which is the thing that we cared about. And so basically what I have to do is I have to find an element, a polynomial here, because I'm working with polynomials, but that may not be needed in general. But say and if I have this polynomial that is fixed by this group, but nothing bigger than this group inside that, then with that I generate all the invariant functions as quotients of this, as a field, basically. And the polynomial that I need to add is this polynomial that I have written here, which basically is a polynomial of xij's, where that is the product of the diagonal times the off diagonal, sum over all I different from j. And and basically this element is what ties the fact that if I do a permutation between diagonals and off diagonals, they have to be matched. Does that make sense? Matching a permutation between off diagonals with diagonals is given by this polynomial. And what this theory tells me is that, well, I mean, we have to prove that this polynomial is fixed only by this group and nothing bigger than this group inside here. But when you prove that, then what you learn is that the field of rational functions that are invariant with respect to this action is given by the symmetric polynomials on the diagonal, the symmetric polynomials in the off diagonal, and this extra polynomial f star that does the gluing of the permutation in the diagonal and the off diagonals are consistent. And basically that's the main Galois theory result for this action. So what does this tell me? It tells me that any invariant function with respect to this action can be written as a function of this, and that, as a rational function of this, and that. So it could be a quotient of polynomials that include polynomials of this form, and that form.
Soledad, so you mean elementary symmetric polynomials in diagonal elements for FD, for example? So we consider all elementary symmetric polynomials for diagonal elements, then all such polynomials for off-diagonal elements, and then we should also use, or we are allowed to use one extra specific polynomial. Okay, right. So this is a theorem, the main result in your paper, right?
That is where the main result of the first part of the paper, and then the second result I'm gonna explain just now.
See. Okay, yeah, thank you.
So in practice, the way we implement this is not using the polynomials. We use this neural network architecture called DeepSets. And basically, the DeepSets is a very nice paper. I imagine that many of you are familiar with it. Basically, it shows you that if you want to write a permutation invariant function, you can write it as you can write it as a function, as a composition of two functions. Say if you have n elements in dimension k, you can write an embedding from Rk to Rl, and then a readout function from Rl to Rs. And every permutation invariant function can be approximated as the readout of the sum of the embedding of each of the n elements. And then they have some theory that tells you that it's universally approximating. And in order for it to be universally approximating, the size of the embedding needs to grow with n. And in the original paper, the growing is exponential. But there's a recent paper by Yusu Wang and collaborators that show that L can be chosen to be of the order of k times n. And so you can have universally approximating deep sets that grow linearly with the size of the input. And so the way we would implement that is like a deep set of the diagonal elements, a deep set of the off-diagonal elements, and then the extra term that we derived using Galois theory. And then the theorem says that if you have a model like this, then you can universally approximate invariant functions of matrices outside an invariant closed zero-measure bad set, with the caveat that the size of the embedding of the deep set needs to be universal, right? So you can have, using the technology by the deep sets, you can implement a machine learning model of this form. And the nice thing about the deep sets and these machine learning models is that you can evaluate it on point clouds of different sizes, whereas the symmetric polynomials, you can't. So that's a nice thing to do. So, okay, so that's for the first part using Galois theory. But as you see, here we have order on n square features because we have to compute the off-diagonal elements. But what we're going to do is we're going to use ideas from low-rank matrix completion, low-rank matrix recovery, to show that actually we can get away with using O of n times d features. And that's the second main point of the paper. So basically, and this doesn't really use the Galois theory. It's just like using some techniques from low-rank matrix completion, you can go from this O of n squared to O of n d and still have this almost universality claim. So the way you do it is the following. So you start with your n points in Rd, and then you consider a function of your point cloud that I'm going to call C of V, that there are going to be like some centers. And these C of V centers from the point cloud, you can think of it as K centers that are OD equivariant. So if I rotate my point clouds, the centers rotate with the point cloud, and they are SN invariant. So they don't really see the order of the points. So one example of how we would implement this in practice is we're going to use the K-means centroids that we're going to, K-means is actually NP hard, but K-means is implemented broadly. An approximation of K-means is implemented broadly and is very efficient in like, these packages, like linear algebra packages, so just on machine learning packages. So I'm just going to think, well, the K-means centers satisfy that. And if the K-means centers are ordered by 2 norm, they're permutation invariant. Right? Because if I apply a rotation, if I apply a permutation, then the centers are like could permute in SK, but if I order them by norm, then there's a unique, it's kind of like a canonicalization of the orbit by SK.
Mm-hmm.
And K here is going to be equal to D, the dimension of the space.
Soledad, by 2 norm, do you mean the Euclidean distance from the origin,
Yes.
say center of mass, to a center of K-means clustering?
Yes. Yeah.
And what happens if you have 2 centers exactly at the same distance from the origin?
Sure, you don't identify them, but that's something that happens with probability 0, like it's measure 0. So we are working. We're working on approximating outside a bad set, and this bad set is a measure 0 set that includes the cases where the D centers have the same norm. Yeah.
Okay.
So how do we do this? We take your point cloud, then we take these K centers, and here K is going to be equal to D, the dimension of the space. And so when we take the matrix of inner products, then we can write it in this form. And this matrix that I have here is a symmetric matrix and has rank at most D. And so from the theory of matrix completion, you can actually recover it using D rows or D columns of this matrix. So what you can do is generically, right? I mean, what you can do is you can take the last D rows of this matrix and then write your machine learning model on the last D rows of this matrix. And there exists a unique reconstruction. So from these last D rows of this matrix, there exists a unique reconstruction that can reconstruct the entire matrix. So any function of the entire matrix is in a one-to-one correspondence of any function of the last D rows and columns. And so you can write your machine learning model based on the last rows of the matrix. And so basically, the machine learning model that you write is a deep set of these C transpose V and a matrix of and a function of the inner products of the last bit of the matrix. So basically, it's a deep set of that and these. And you can see that if you write your machine learning model as this form, then the machine learning model obtained can universally approximate invariant functions on point clouds outside an invariant set, the bad set, which is invariant closed and zero measure bad set. And these the cases that you mentioned were actually inside this bad set. Yeah. So this idea suggests two different ways of dealing with invariant functions on point clouds. One, the first one using Galois theory, we thought it more in like as a machine learning model on symmetric matrices that are not necessarily low rank, because you use O of n square features, so kind of like another way of thinking functions on graphs. And the second, this model, we thought of it as like a model for point clouds, because you only use order n times d features to construct them, these functions. And we have some simple experiments on molecular property prediction on like a standard simple benchmark data set. And basically, we show that the model performs reasonably well, though we didn't really optimize it. We just thought of it as like a proof of concept, and we saw that it made sense, but we didn't like beat the state of the art in any problem of significance in this field. And then we also did some test on these point clouds from this model net 10, which is like point clouds that represent furniture. And we did some regression, and then we saw that the regression based on this model actually performs reasonably well. The target that we use here was some distances between point clouds that is invariant with respect to permutations and rotations. And I can talk more about this, but basically this tells you that, well, the target was this Gromov-Wasserstein lower bound, and we obtained that that doing this k-means relaxation of this model actually doesn't lose much of the performance with respect to the other model. And so let me give you some conclusions and tell you an open problem that I'm thinking about that is related with this. So basically, we're saying the whole point of this talk was telling you that we can express invariant functions on point clouds via these lightweight invariant features that we constructed using Galois theory and using tricks from low-rank matrix completion. And the future work that I'm interested in is actually applying these ideas to real cosmology problems. For now, we only the paper that we have out only does the mathematical theory and some toy experiments, but actually we want to see whether these ideas actually are useful for more important scientific problems. There's a nice connection between Galois theory and the Stone-Weierstrass approximation that I think is a story worth telling. And also these ideas we just talk now have to do with invariant functions, but we have some ideas on how to extend these ideas to equivariant functions, so not just invariant. So if I have a group acting on the output as well as the input, then can we write the equivariant functions with respect to that? And we have a paper in the notices of the AMS explaining how do you go from invariant function to equivariant functions. And this doesn't really apply exactly. I'm not going to go into the details in the interest of time, but we have that. But the thing that we're doing is not a direct application, but we will need to like change some ideas here. And I think that there's there's some rich mathematical theory to investigate here. And this is my postdoc, Ben Bloom-Smith, who was the first author on this paper, and also did this. He's an invariant theorist, and he has been exploring the connection between invariant theory and machine learning more broadly. So I'm going to end here. I'm going to thank you and giving you the references, and the paper that I presented today is on arXiv. And yeah, that's it. Thanks.
Thank you, Soledad. So please thank Soledad for the nice presentation. Okay, so I'll stop the recording and